All right, sorry, I'm just going to repeat myself because I forgot to hit record. Yeah, so surface tension, this typically is something you see with water. This is the ability of a fluid surface to shrink to the minimum surface area possible. This has to do with the intermolecular forces for water. Water has high intermolecular forces because, and you learn this in chemistry 1120, it has London dispersion, dipole, and hydrogen bonding. Now, you don't obviously need to remember that for chemistry 2420, but these attractive forces between water molecules means it has a high surface tension. So what, in greater detail, what is surface tension? Well, a molecule that's in contact with a neighbor, meaning another molecule of the same chemical, would be in a lower state of energy than if it was alone. So molecules next to each other are in a lower, which is a better state of energy than if it was by itself. The interior molecules, so if you're looking again at a bead of water, so this is like, all of these molecules are in the bead of water. The interior molecules inside the water have as many neighbors as they could possibly have. But the boundary molecules, the molecules out on the outside, they do not have as many neighbor molecules. So they have a higher state of energy. So what the liquid tries to do, what the chemicals try to do, is they try to minimize or reduce their energy. Everything wants to be in a lower state of energy. So the liquid, to minimize that, the boundary molecules needs to be minimized. The molecules themselves try to, again, lower all of their energy state and have the smallest boundary possible. Oops, sorry about my pen there. So as a result of that, a surface will assume the smoothest shape it can. The smoothest shape, typically a sphere or a rounded shape. There is a mathematical proof out there that proves that the smooth shape minimizes surface area. So instead of, a bead of water being, craggly and mixed up like that, it tends to be smooth. And I mentioned to you guys yesterday that you could try this in your house, in your kitchen right now. You could get a glass of water and fill it to the top, and then just add some extra water, just a couple of drops, and you would see the water kind of dome over that glass. It's trying to create the smoothest outer exterior boundary that it can to minimize surface area, because that gives it its lowest possible energy. What this ends up doing is creates a surface that is tense or has, high surface tension. And this part of this is why water and oil, for example, don't mix. The big part of that, of course, is because oil is nonpolar and water is polar, but the surface tension really keeps them separated. If, and we'll learn this in the next section, you could find some sort of chemical or mechanical way to reduce the surface tension, to break it, to break apart the attraction that water molecules feel for themselves, you could make a mixture, or in the case of oil and water, it's called an emulsion, which we'll talk about in 5 or 10 minutes. So your outcomes mentioned you should also learn the term interfacial tension. It's the same thing as surface tension. So you don't need to, memorize both terms or anything. But separation of oil and water is caused by this tension because the liquids are dissimilar or not the same. So oil is nonpolar, water is polar, so they are immediately not attracted to each other, and their surface tensions create this separation between them. It typically, if like this example, if you let that sit for 10, 15, 20 minutes, it would settle to be like a nice straight line. All right, so that brings us to this section, my favorite section, 5.13, surfactants and emulsions. I love this. Now, I won't get this done today, but this is wink, 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 an important section, something you should definitely know for like a final exam, and we'll talk about it right now. All right, so first, we're going to talk about mixtures of solutions. And you guys did this back in Chemistry 1120. You looked at, I can't remember what lab it was, maybe lab 5? No, lab 8. Yes, lab 8, you looked at solutions and different types of solutions. We had saturated, supersaturated. We're kind of going to talk about that today, but a little bit more in depth. So a colloid is a mixture in which one substance of microscopically dispersed insoluble or soluble particles is suspended throughout another substance. So in simple words, a colloid is a mixture where one substance is suspended or spread throughout another substance. Sometimes the dispersed substance is called the colloid itself or the colloidal particle. One example of a colloid, sorry, that's true, and I'm just reading the chat there. It says, I keep saying it's my favorite in the beginning, at least from section 5.10. Yeah, I'm pretty repetitive there, but it's true. One example of a colloid that you guys would see in everyday life would be milk. Milk is made up of like two main things. You have kind of like the water, or I think they would call it like, I mean, some in kitchens or recipe books, they might call it the buttermilk or the milk or the liquid itself. And then you have the milk fats. So skim milk is different than say whole fat milk or, whipping cream, for example. So a colloid, a good example of that is milk, is milk where you have like this liquid and then the milk fat is suspended throughout. That's why maybe like for old bottles of milk, they tell you to shake it before you use it. I guess another example you could think of for a colloid would be a juice, where you would have like the liquid and then the pulp of the juice spread throughout. It's not so much a microscopic example, but these are just simple ways to think about colloids. And we're going to look at a bunch of different examples of this soon. So unlike a solution, where the solute and solvent are just in one phase, meaning the solute and solvent are mixed together in the same phase, a colloid has a dispersed phase. Particles are suspended in a medium. So the dispersed phase are the particles suspended in, or like suspended means held in the continuous phase, the medium. Again, like think about juice, like fresh orange juice. There's the liquid medium and then the pulp. And the pulp is usually suspended in that liquid, but sometimes you have to shake it to help that dispersion. One thing that's kind of weird about my juice example, though, is to qualify to be a colloid in chemistry, the mixture shouldn't settle, or it would take a very, very long time to settle. So milk is probably still the best example of that. Think about like if you took a handful of sand and you put the sand in the water and you shook it up. For maybe 5 minutes or so, the sand would be suspended in the water. But eventually, the dense sand particles would sink to the bottom. So by definition, we wouldn't really call that a colloid. We would call that like a heterogeneous solution where the sand and water are completely different. Milk, however, the milk fats, the creamy part, the fat molecules in the milk stay mixed for days. When you go buy milk at Carrefour or Lulu, Almira, whatever, milk is usually good on the shelf for a couple of days. But if you left milk long enough, sometimes the fat can separate out. I guess a good example of that, and this is if any of you cook, is a can of coconut milk. Because canned foods are typically old, they're left for days, weeks, months even. Sometimes when you have a can of coconut milk, the milk fat is separated and it rises to the top. So I don't know if you've ever done this or if you're cooks, but typically when you use coconut milk, you have to shake the can first to redisperse the solid. It's still a colloid though, because coconut milk could be good for days. So the definition of a colloid is the mixture should not settle. The dispersed phase shouldn't sink to the bottom for really quickly. The other parts of this definition are the dispersed phase particles should be very small, which is kind of why my juice example might not work, because the pulp in juice is quite large. So typically in a colloid, the molecules or dispersed particles are small, between 1 and 1,000 nanometers. That means that you can see them with a microscope, but some of them are so small you might need special equipment like an electron microscope. Optical microscope, I don't know if any of you have done biology. I don't think you need to do biology for your program, but optical are like the tabletop classic microscopes. So this is an important slide, very important. These are the types of colloids, and you can see that the types of colloids go through all three phases: solid, liquid, gas. So I'll just explain this in 1 second. All right, so have a look at this chart, see if you can figure out how it works. I will explain it, of course. Just give me 1 second. All right, so dispersion medium, that would be the kind of like you could picture this like the solvent. It's really not a solvent or solute situation, but it's a good way to think about this. So the dispersion medium is kind of like the chemical that's in the bigger amount. The dispersed phase is similar to the solute or the chemical in the lesser amount that's spread throughout the medium. So if you had two gases, we would not call that a colloid. That would just be a homogeneous mixture or solution, I guess I should call this. So it's definitely not applicable. We would call this a solution. So solutions and colloids are not the same. Okay, well, what about if your dispersion medium was a gas and you spread a liquid through that? Well, a liquid dispersed through a gas, the best example I could give you is a cloud. Clouds are made of liquid water dispersed in the air. We call those in chemistry aerosols or liquid aerosol. If you have a solid dispersed in a gas like smoke would typically, like black smoke, would typically be solid carbon particles just suspended in air. We would call that a solid aerosol. So aerosols are things that are suspended in gas. If it's a liquid, it would be like a cloud. If it was a solid, it could be like smoke. You guys saw smoke in lab number 4. Yeah, even I guess a cigarette or candle smoke would be the same. But in lab number 4, you burned hydrocarbons and you saw black smoke. That was solid carbon particles dispersed in air. All right, my favorite part or my favorite section of this is the liquid because this is kind of where cooking comes in. A lot of cooking techniques might, like especially if you guys go to like a fancy restaurant, cooking techniques might be or are related to like foams and emulsions. An emulsion, also, well, okay, sorry, let's start with foam. I'll start on the left. A foam is when you have a predominantly liquid medium but there's a gas dispersed in through that. So an example, and you guys could go do this right now, you could whip up an egg white or whip cream. By whipping, you take a whisk or a fork and you're introducing a gas, the gas being air, into a liquid medium. And as more and more air gets suspended in the liquid, it begins to foam. The volume increases, it becomes lighter, there's bubbles. Foams are gases that are dispersed in liquids. And the easiest example is whipped cream. One of my favorite ones is an emulsion. Emulsions are how people make vinaigrettes, where you have oil and vinegar mixed together. They should not mix, but we managed to make them mix in the kitchen. Milk is another one. Typically, emulsions are non-polar substances, non-polar liquids dispersed, or sorry, non-polar or polar liquids dispersed in the opposite medium. So that's a really important thing to think about. If your liquids are both polar or your liquids are both non-polar, we don't call it a colloid. We would call it a miscible. So a space, new word, miscible solution. Miscible means mixable. Immiscible means the solutions or the chemicals do not mix and it's not a solution. Remember, the definition of solution is it's a homogeneous substance. So if you take two liquids that are immiscible, like oil and water, they separate. But if you can mix them together in some way so that all of the oil is dispersed in the water or vinegar or milk, it would be called an excuse me, an emulsion. And this is really important for oil and gas. So these two are very important for oil and gas because think about it. Gas is a liquid, or crude oil is a liquid, and inside of that you could have water or air or other gases, hydrogen sulfide. So these two are the ones you need to know. Wink, wink, wink. I'll go a little quicker now because these aren't as important. A sol is when you have a solid dispersed in a liquid phase. Pen ink is one of those. So the color in the pen ink is a liquid. The color is a solid, so that would be called a sol, S-O-L. All right, and the last part of this table is solids. So when you have a gas mixed with a solid, you might get something like a solid foam, like styrofoam. These aren't as important. When you get a liquid dispersed in solid form, you get a gel, like jelly or jello. I don't know if you guys eat jello here. I've never really seen it outside of Megamart, but Jello, a famous kind of American brand of food, is when you have a liquid dispersed in a solid. And then finally, a solid dispersed in another solid would be called a solid sol, S-O-L. And that's like colored glass or stained glass would be an example of that. But the big ones you need to know are here in the middle, foams and emulsions. All right, let me see how far I want to go today. College stability. Okay, I think what I'll do today is I'll get up to soap. I'll get up to slide 100 and then we'll stop. So just a couple more slides. The soap part here, This is what lab number 6 is about, as well as colloids. So hopefully this weekend I can film your lab. I'll pop into the campus on probably Saturday afternoon and film myself doing that lab for you guys. So you'll learn a bit more about soap next week. So you don't have to worry about the lab this weekend, but I should have it filmed by Saturday. Anyways, all right, so a couple more slides. As particle size, so again, we're talking about colloids, mixtures. As particle size decreases, surface area increases because of how it's a function or mathematical function of volume. So when you have smaller particles, their surface area tends to increase. Um, Let me finish. Sorry, there's a question in the chat I'll get to in a minute. So in the colloidal size range, 1 to 1,000 nanometers, there's a lot of chemistry or scientific interest in how the particles interact. Most colloids that are commercial products, meaning like things that you would buy at Almira, are designed to remain there for a long time. So milk, even coconut milk, shampoos, whipping cream, all that stuff. Commercial products are designed to last for a long time, but even then, you might have to shake the product before you use it. And the example there I would give you is milk or whipping cream. A lot of times you have to shake it before you use it. All right. So milk is an example of this. It has liquid butterfat molecules dispersed in water. Milk is an example where there's a chemical process called homogenization. Very fun word to say, homogenization, used to reduce droplet size so that the mixture or the colloid stays suspended for a long time. So there's chemical processes done commercially to help colloids be stable. So that brings us to stability of colloids. Oh, and sorry, I'll get to that question in the chat. There are 7 labs, 6 is online, and the last lab as of now will be on campus. Lab 7 is, as of now, it might change in the next week or two, but lab 7 would be on campus. But there are 7 labs. So you have to do lab number 6, which like I said, I'll have filmed this weekend. And then there's one more and we're done. Whoop. The last lab is on the end of this course. It's about mixtures and alcohols. So that'll be a little bit later. All right, so the stability of a colloid is defined by the particles remaining suspended. Stability can be hindered, which means like harmed or ruined or, negatively affected by aggregation and sedimentation. These wink, 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 oops, sorry, words you need to know. Wink, wink, wink. I'll talk about this on the next slide. I have an image for this. So stability, you can ruin a colloid or break a colloid by aggregation or sedimentation. And this is all driven by chemicals' tendency, not just a colloid, but every chemical's tendency to reduce surface energy. Everything wants to reduce its surface energy. Reducing the surface energy, surface tension, help stabilize the colloid. So a lot of colloids don't want to be mixed all the time. They want to settle and kind of separate out, which I will show you here. The left is an example of a stable colloid. Okay, so it's been mixed, like this would be like milk you would buy at Almira. It's been mixed. The suspended particles stay there for a long time. But what can happen over time is these particles can become unstable due to 2 factors: aggregation and sedimentation. Now, remember, when the particles are all spread apart, their surface area is much bigger. Like, okay, so for example, just imagine this shape of a molecule. right? So I have like two molecules bonded together. Where they are touching means there's no surface. So this has less surface area than if they were separate. Remember, surface area is the area on the surface. So if the two molecules are bonded together, they're touching each other, there's less surface available. Molecules or colloids, any chemical really, wants to minimize surface area. So one of the ways a colloid can become unstable is aggregation. Aggregation is when the molecules begin to join together, they aggregate and to reduce their surface area, and they become larger and larger, and they're not as mixed in the colloid. Sorry, just gonna check something out. Yeah, so the English definition of aggregation is the formation of things into a cluster. So aggregation is when these chemicals bond together to reduce surface area. Sediment, so aggregation, they group together. Sedimentation is when they settle at the bottom. So sedimentation over time, some of these molecules can settle, or kind of, you can almost think of this like a precipitate, but they settle at the bottom. So remember, the key for a colloid is all of the molecules should be suspended in the solution. And two ways to break that is if they group together or they settle at the bottom. And you need to know that, wink, wink, wink. All right, I think I'm almost done. It's 107. Okay, 3 more slides and I'll finish, and this will be pretty quick because it's just some definitions. Also, some terms you should definitely know for like multiple choice purposes. Okay. 4 definitions, but they're actually pretty easy to remember. First, before I explain these definitions, you should know the words phobic and philic. Phobic means to be afraid of something. So if you were, what is it, arachnophobic, that's a good movie, Arachnophobia, really cool movie. But arachnophobic, that means you are afraid or you have aversion to spiders. So phobic means to have a fear. Oops. Philic means you have an attraction to something. So lyophobic means substances have no attraction for each other. And in particular, for a colloid, it means the dispersion medium and the dispersion particle. So you can think of it like the solvent and the solute. They have no attraction to each other. Lyophobic, the dispersion medium and the dispersion particle are not attracted. Polar, nonpolar, you can think about it like that. Lyophilic means that the dispersion medium and the dispersion particles do have an attraction for each other. So lyophobic substances are easily precipitated. Lyophilic substances are not easily precipitated, which means they make good colloids, good mixtures. All right, and then 2 more definitions, and I'll kind of explain this a little bit more next week, but hydrophobic and hydrophilic, it's exactly what it sounds like. Hydro meaning water, phobic meaning fearing. Hydrophobic substances, like oil, are repelled from water. They are afraid of water. Technically, they're not repelled from the water. They're just not attracted to it. So it's, it's not like two opposite sides of a magnet, or sorry, two of the same sides of a magnet where they literally repel each other. Hydrophobic substances are just not attracted to water whatsoever. Hydrophobic molecules are typically nonpolar, so they would prefer other nonpolar things. So examples of this are alkanes or oils or fats. Oil, right? Oil and gas is a hot wink, 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 nudge, nudge. Hydrophobic substances are oil or include oil and gas products, typically alkanes and things like that. Hydrophilic substances are substances that are attracted to water. Excuse me, they are usually polar or ionic. This could be things like salts or sugar, or alcohols are polar. Carboxylic acids are polar. These are attracted to water. Hydrophilic means water loving. Hydrophilic substances, some hydrophilic substances, are not soluble, so you could make a colloid out of them. But typically, when you mix two hydrophilic substances like water and, say, a carboxylic acid, they don't form a colloid, they form a solution. And just the last thing I'll mention today, and then that's it, is just if you could learn one thing today, is to wrap your head around the difference between a solution and a colloid. A solution is a homogeneous mixture where you cannot tell the difference between one phase and the next. They cannot be separated easily, like a little bit of salt dissolved in water. Without, using distillation or heating it up, it would be very hard to separate that out. Colloids are not pure homogeneous solutions. They are mixtures where the particles are suspended in a medium, but they can be separated just by leaving them. So like if you had a glass of salt water and you closed it up, sealed the like a jar with a lid, that would stay the same forever, right? The salt and the water would stay the same in the same solution literally forever, unless like you let it evaporate or something. But if you had it in a closed system, it's fine. It's good forever. But if you took milk, so that would be milk fats suspended in a liquid, and you let that sit in a closed jar for a month, and again, like think about a vacuum sealed closed system. It's not going to go moldy or anything like a can. It would separate. So the difference between a colloid and a solution is typically over time that colloid will break apart or separate. And okay, and I lied. I'll say one more thing. Oil and water can form a colloid. Oil and gas, like as in like, methane or carbon dioxide or hydrogen sulfide, can also form a colloid. Not a solution, but a colloid. And they would be respectively emulsions, liquids in liquids, or foams, gases in liquids. So we'll talk a little bit more about that tomorrow. I'm very excited tomorrow, or well, not tomorrow. Tomorrow's Friday, but I'm very excited next Monday in class to talk about soap. There is literally no better time to talk about soap than coronavirus COVID time. So this will be kind of fun on Monday. We'll talk about like why soap works. How does soap get rid of germs? Does it kill germs? Like it's kind of interesting. So guys, that's it for me today. Thanks for coming, Abdullah, Ali. I have AZ, Bashir, Lena, Naim, Saud, Saif. Thank you all for coming. Sorry, it's a little bit boring. It's mostly me talking because there's no practice problems, but hopefully you'll find at least Monday's class interesting. And I'll have your lab number 6 filmed this weekend. Like I said, I'm going to go into work on Saturday, film the lab, and then I'll make the post probably Saturday or Sunday. So you should have your lab by at least Sunday. All right, guys, any questions? If not, have a fantastic, safe weekend. Woo, it's Thursday.